Hey guys, this is Mr. Goya coming at you here. Hey, we just started, the other day we just started our momentum unit, and we got through the first, I think, a couple pages there, and first 3 pages, I guess. Today we're going to look at really page 4, and I think possibly go through maybe page 7, I guess, and work a few more problems. So we have been discussing momentum, right? We said momentum, this idea of momentum, which is often given the symbol P, it's the product of mass and velocity. Okay, so we take an object's mass, that's in kilograms, and we then multiply that object's mass times the velocity. And we'll put those in meters per second unit. We multiply those two things together, and then we get this idea called momentum. This concept of momentum really comes from Newton's second law. We derived this kind of equation for you yesterday, or the last day we had our notes, and we really said then that this Ft, which we call our impulse, is really equal then to the change of momentum, or a final momentum minus an initial momentum, and that's equal to this Ft. This Ft then is called the impulse. This Ft is a product of a force on an object and the time that that force acts on that object. We said then we could do follow through like in sports, and we can then increase an object's momentum, i.e. its velocity. When we follow through, we keep that force on that object for more time. Or we could talk about then decreasing an object's momentum if our impulse is negative. We said that that was pretty important then when we got to, car safety and things they develop on cars like airbags, etc., that lead us to this idea here where if we could keep the time greater on that object that force is acting, we can make that force smaller. And having smaller forces is better when we're talking about people, for example, or automobile wrecks. We're going to go on to page then 4. We did a few sample problems for impulse momentum. We're going to go on to page 4, and we're going to talk really about the second kind of gist of this unit, and that's the idea of collisions. So when we talk about collisions, we're talking about one object maybe hitting another object. All right? I'm going to show you a quick little video first. This came from kind of a advertisement on TV. Maybe you've seen this commercial. It's ran for a few years, I guess. And let me show this to you now.
Definitely. That's television. Check it. Ooh.
Need a better battery? Get an Interstate battery. Outrageously dependable.
So they had an Interstate.
Okay, what'd you think of that commercial, huh? Have you ever been in that situation before where you're either you were on ice or you didn't have really enough friction there, and you had a hard time stopping? You can kind of get the feeling of those kids in that commercial, Now, what we're dealing with then are collisions. One object hitting another object, all right? And what we can say then is that we can transfer momentum. So one object has momentum, and it can then transfer the other. This transferring of momentum then is the basics of what's called the conservation of momentum. Conservation mean that we don't really lose any, as long as we neglect any sort of friction and external forces. All right? Now, there really are 4 different types of problems that deal with momentum conservation. And the first type we're going to deal with first is what's called a one-dimensional, perfectly elastic collision problem. What perfectly elastic means is we don't lose any energy, no loss of energy in the collision. All right? Now, perfectly elastic is somewhat theoretical. Most collisions have some loss of energy. However, it's good to think about perfectly elastic. It's kind of like when we were talking about, sometimes we have to ignore some stuff to make the physics a bit easier. And this is one of those scenarios. So for example, when 2 balls hit each other, there'll be a little bit of sound energy. Like if you're talking about playing pool, be a little bit of sound energy. So consequently, it's not perfectly elastic, but it's pretty close. All right? Now, so perfectly elastic, if you could think of maybe a word, you might say it's perfectly bouncy. The next one's just kind of the opposite of that. It's inelastic. So we have then 2 objects hit each other, and then they stick together. Oops, let me spell that right there. Stick together after the collision. We'll work a few of those problems. These are called perfectly sticky, collisions. You probably have heard the word recoil. Well, recoil basically is you take one object really, and then that object kind of splits into 2 parts. Or there's, like if you've heard of recoil with like shooting a gun, the bullet goes one way and the gun goes the other. But initially it was kind of all one unit. So it was all one unit, and then one thing goes one way, the other thing goes the other way. That's what's called a recoil problem. Then we also can deal in 2 dimensions. So maybe we have one object going one direction and another object going another sort of vector. And then they come together and collide. In 1 dimension, both objects are traveling along the same grid, same axis, same line. This is, for example, this is a one-dimensional collision problem. 2 dimensions, we have to deal with the x and the y. We'll work a few of those problems. Okay, probably the easiest thing to do is to really just go to page 5 and work a few problems with you. Okay, now, again, there's kind of a pattern on how you might want to work these problems. We like to draw pictures, and then there's some symbology that I'm going to kind of work with you on. So what we've got is this marble. Okay, there it's 0.015 kilograms. Okay, it's a pretty tiny marble. It's moving to the right. So this would represent then the mass, right? And then this would represent the velocity. So this marble is moving to the right. It makes an elastic head-on collision. Okay, that means it's transferring its momentum with no loss of energy to this other marble. So it's hitting this other marble. Again, we have the mass of the second marble, and the second marble is moving at its velocity, and it's moving to the left. Okay, now this stuff's important. Direction, all right? Because again, direction then is important with vectors. So let's kind of draw, what we do on these is we kind of draw a pre-collision picture, and then we draw a post-collision picture. Okay, it says after the collision, the smaller marble moves to the left at its velocity, and we'd like to figure out the velocity then of the larger marble, the shooter marble, all right? So what we have then is this one marble. Usually with these objects, we might call one object A and the other one object B. That's a good way of differentiating. So this one marble A has this mass. So I'm going to write down MA is 0.015 kilos. And the velocity of A is 0.225 meters per second. And that's going to the right. So I'm going to draw myself a little picture there. All right. This shooter marble is a little bit heavier. It's a little bigger. 0.030 kilos. And it's moving to the left. Now I'm going to call that negative velocity because it's acting to the left. And it's then 0.18 meters per second. Now, so what's going on then after the collision? Well, the small marble, we have this collision, and the small marble is basically sent backwards. Okay? Now, we know it's really the same mass. Okay? It didn't lose any mass, but its velocity, and what a lot of textbooks will do is they'll put a little dash there. That's called prime. Velocity prime, that means the after collision or post collision velocity then of A is going to be the negative 0.315. Now, we're not really sure what B does. So velocity prime B, that's our question mark. We're not really sure about that, okay? So here's the elastic collision equation really. The momentum of A plus any momentum B has pre-collision, that will equal then to the post-collision momentum, post-collision prime A plus the momentum of the second object post-collision prime, all right? Momentum of A plus momentum of B equals the post-collision momentum A plus the post-collision B. All right? Well, momentum again is mv. So we would write then ma va plus mb vb equals to ma va prime plus mb vb prime. Yeah, that makes sense? Okay? Now we're ready to really put our numbers in. So we've got 0.015, that's in kilograms, times its velocity, 0.225, plus 0.030, times its velocity. Be careful, you got to have the negative sign in there, all right? That's going to equal then to the mass of A times its velocity, that was negative 0.315, plus the mass of B, 0.030, times, I'll just keep the unknown then, VB prime. All right? That's what we're trying to find here. We can get its velocity then. What we have to do is multiply these and then add them up and then subtract this number. So again, a calculator's pretty handy to have here. All right? You can follow my calculations. Let me turn it on. So 0.015 times 0.225, okay, 0.003375. We've got a negative on this side, 0.03 times my 0.18, okay, minus 0.0054. Let's figure this one out, 0.015 times 0.315. Okay, so that's going to be negative 0.004725 plus 0.030 VB prime. Okay, we can subtract this. We can put this on the other side by adding it. Do you understand the algebra? Okay, I'm kind of running out of room, so I'll kind of keep it going down here. So I'm going to take 0.003375 minus 0.0054. I get my left side. I'm going to add this to that. So I'm going to add it, put it on the other side. So I'm going to really add 0.004725. Okay, I get 0.0027. I want to divide that then by this coefficient, and that should be VB prime. Again, the symbology would be what's the velocity of ball B, object B after the collision. And I get then a velocity of 0.09 meters per second. Okay, now that's positive. We get a positive number here. That's telling me then that this is moving to the right, all right, with 0.09. All right, it was moving to the left. A and B have this collision. Now A goes the other way and B goes to the right. So both objects here have this collision and they both move then opposite in the direction that they started. All right? You want to give number 2 a try? I'll kind of help you set it up here. Okay, let me change colors here. So we're talking about bowling. Bowling is a ball hitting all these pins, and it's not perfectly elastic, but it's pretty close. Okay, so we've got this big bowling ball coming down and hitting this pin. Okay, this is a pre-collision picture. All right, and we'd like to then figure out really what happens then afterwards. Okay, pre and post. So we want to call this maybe A and B, so we know that's 5 kilos, that's the mass. Okay, so this ball's rolling down at 2 meters per second. Okay, we have it going to the right. Now, this pin is not moving. Okay, it's 0.4 kilos, but its initial velocity is 0. All right? Now, so if the ball leaves the collision at 1.5 meters per second, okay, so this velocity here is of the pin after the collision. So we're looking just at a collision between the bowling ball and one of the pins. All right? So you kind of know what to do. So if you're having trouble, just stick with me here. Say we're saying the momentum of A plus the momentum of B, oops, that should be a P, momentum of B is equal to the post-collision momentum of A plus the post-collision momentum of B. All right? Or MAVA plus MBVB equals MAVA prime plus MBVB prime. Okay, you understand all that symbology? Again, the primes mean post-collision. Okay, so 5 kilos times its velocity plus its mass of the pin times its velocity. That equals to the mass of the pin, of the ball, the mass of the ball, 5, times its velocity, plus the mass of the pin, 0.4, times its velocity, which we're not sure about. All right? So 5 times 2, don't even need a calculator, 10, plus 0.4 times 0, that's just 0. That equals 5 times 1.5. Okay, do that in your calculator if you need to. Okay, that's 7.5 plus 0.4 times VB prime. Put this on the other side. Okay, so we'll have 10 minus 7.5, and then divide that by your 0.4. We get then a velocity of 6.25. It's pretty interesting, really. So this thing's moving pretty fast. It hits the pin, and the pin goes flying away at 6.25. All right? It didn't have as much mass, so it got a lot of that momentum now as velocity. All right? This represents then elastic collisions. This equation that I've just written here, okay, this equation, let me rewrite it here. PA plus PB equals to PA prime plus PB prime. Okay, P again is a symbol for momentum. This is what's called our elastic. It's our elastic collision equation. All right? Our next equation will be a little different, and we'll do a few of those problems on the next page. So we'll go to page 6. Okay, so now I'm on page 6, and I want to work then a couple of what are called then inelastic collision problems. So we have two objects, they collide and then they stick together, okay? And there's quite a few objects that actually do this. After the collision, they kind of stick together. Some auto wrecks are this way, where the bumpers kind of lock and then they stick together and move off at some common velocity. The equation is going to be a little different. Again, that's an inelastic collision. So two objects collide and then stick together, okay, to form kind of one object. So again, we basically can show diagrams pre and post collision. So it says one train car with the mass of 600 kilos. So again, we can call this A, we can call that B, 600 kilos. It's moving at a velocity of 1.5. See, these little train cars have these little couplers. When they hit each other, whoop, when they hit each other, they can kind of stick together. They kind of lock up there. The second car is a little heavier. It's got a mass of 700 kilos, but it's stationary. All right? Its velocity is 0 at the beginning. We have a collision, and now we really then have one object moving in common. Okay? It's definitely not going to now move at 1.5 because now we have then a combined mass here. So let's think this through really and come up with what we call our inelastic equation. Okay, so we've got the momentum of one object plus the momentum of the second object. Okay, and it's going to then equal to some sort of a common momentum prime. All right, the masses will have to be added. So we could say MAVA plus MBVB, that's going to equal then to MA plus MB, and I'm going to put that in parentheses, all right, times some sort of common velocity. And I'm going to put a prime there, and that tells us it's after the collision. V prime common. We write common there because that's telling us the whole unit, the whole thing is moving at one velocity. So what we've got is 600 times its velocity plus 700 times its velocity. It happens to be stationary. That's going to equal to the combined masses. That'll be 1,300 times that common velocity. Now it's just working through the algebra. Okay, 600 times 1.5. Okay, calculator comes in handy. 600 times 1.5. That's 900. We get 0 there. Okay. We want to divide now that 900 by 1,300, and that will give us our common velocity, around 0.69. That's going to be V prime common, 0.69 meters per second. And that's the answer there, right? So this car was approaching at 1.5 meters per second. It links up and has a collision. Now this heavier thing then is moving at 0.69. Okay, you want to give this one a shot? Okay, I can kind of help you too. There's one object. It's moving at a velocity and it's got a mass. Then it's colliding with this object moving to the left. Again, we have to be careful with the sign there. And then we have some sort of a common velocity. All right, so let's write down our inelastic equation. MAVA plus MBVB equals to MA plus MB expression, V prime common. Okay, let's put in our numbers, all right? 1.5 times 2 plus 2.5, that's the mass there, times minus 3. That's going to equal to the combined masses, so that'd be 1.5 plus 2.5, 234, times our unknown velocity. You see how helpful this is to get velocities? Again, it's, you know, we know there's ways from Galileo, some equations, how fast equation, etc. But this is just another technique. to get velocities of objects. So what we have is 1.5 times 2 minus 2.5 times 3. Divide that by 4. We get then a common velocity of 1.125. And that's negative, kids. Remember, the velocity being negative just means it's acting to the left. All right? So this would be velocity acting to the left. All right, so there's a couple of examples of inelastic collisions. Now we're ready for kind of our last page, and that's going to be recoil problems. All right? And we've got a couple examples there. Okay, so what we said recoil is we basically have an object, and that object then splits up into two. All right, one goes one way, one goes the other way. So like if you got recoil from a gun, the bullet goes one way, the gun is pushed the other way. That's recoil. A lot of examples again, really. But typically what we use is the elastic equation. Okay, this was the equation we got from page 5, right? So let's read the problem. A baseball player takes his pitching machine out to a frozen lake to observe the effects of recoil. Okay, he's going to do on the lake because there's not much friction there, and you can kind of see what the recoil does. So he places the 50-kilo machine on level ice. The machine fires a baseball with the speed, and we'd like to get the recoil velocity of the machine. So the baseball goes one way, and the machine goes the other way. And we'd like to figure out, well, what velocity is that? Well, so we've got this sort of machine here. It's got a little opening. It spits out baseballs, right? So, but initially, nothing was kind of moving. So in my kind of picture here, the baseball's kind of in the machine. So initially, there's no motion, right? The baseball then goes one way, the machine goes the other way. So this is like a pre-collision and a post-collision picture. But initially then, there's no velocity for either object. So we can say that's 0 on the left side. Does that make sense? This stuff is 0. There's no motion initially. Okay, let's call the machine A, we'll call the baseball B. Well, the mass of the machine is 50. The velocity then of the machine we're not sure about. We want to figure out what that is. The baseball then, we've got the baseball going to the right, and it's 0.15 kilos as it's moving at 36. All right, do you see how to work this out mathematically? Okay, calculator, we'll multiply these things, 0.15 times 36. Okay, that's 5.4. I want to put it on the other side, really. Okay, and it becomes a negative. When I do that, I want to then divide by 50. I get then a velocity equals to negative 0.108. Okay, that's my answer. Now, do you understand what that means? Okay, the ball's moving 36 meters per second to the right. The pitching machine has a velocity much, much, much less than that, right? Because it's so much heavier, right? It's moving then to the left. We got a negative. So again, one object moves one way, the other objects move the other way. You want to try the next one? Okay, it's our last problem that we'll do on these notes, all right? Okay, you see this in skating too, right? Two skaters push off of each other. Okay, again, we're neglecting friction. Okay, the woman has a mass of 54 kilos. She's moving at 2.5. Okay, the man's at 88. We're not sure then his velocity. So let's call her A and let's call him B. Okay, we're not sure of his velocity. We know his mass. So initially, they're starting from rest, right? So I can say then MAVA plus MBVB equals to MAVA prime plus MBVB prime. Okay, we can say all this is 0, right? Okay, the woman pushes off her mass times her velocity plus the mass of the man times his velocity, which we're unsure of. Hey, now does it make sense if both skaters were the same mass? They push off each other. One would go one way, one goes the other way at the same velocities, right? Just opposite direction. But in this case, the man's more massive, right? That means he should then move at a slower speed. Well, you take 54 times your 2.5, put it on the other side, divide that through by your coefficient, divide through by 88, we get around negative 1.53, right? I get negative, meaning it's the opposite direction to the woman. All right, that makes sense? So that's a recoil problem. So what have we looked at? We've looked at then collisions. Okay, momentum is conserved, meaning that the momentum of objects pre-collision equal the momentum of objects after the collision. Okay, we talked about elastic collisions. Okay, these are bouncy. We have no loss of energy. Okay, these are pretty theoretical, right? Generally, with most collisions, you'll lose a little bit with energy. Okay, it doesn't mean we can't still use these equations. They're still good things. Okay, the other type's inelastic. Okay, so there was our elastic equation. Then we have inelastic, where they stick together after the collision. And then we also have recoil. Okay, that's really the major three types of problems. Now, we can also work in 2 dimensions, and we'll do that in another video. We'll talk to you later, kids. Bye.